Hello students, in last lecture we have studied LP space and matrix defined on it. Also Kn, where K is set of real numbers or complex numbers, on that also we are defined DP matrix where P lies between 1 to infinity. Today we will see other classes of objects and matrix defined on them. So today we'll see L infinity space. What is L infinity? L infinity is class of sequences of real number xn such that xn is bounded sequence. Is bounded sequence. For x bar and y bar belongs to L infinity, we'll define D infinity matrix. D infinity of x bar y bar as supremum of mod of xn minus yn 1 less equal n less than infinity. Then we have to prove that D infinity is metric for L infinity, and L infinity with this D infinity is metric space. So firstly we have to check whether D infinity is well-defined function. Step first, to check D infinity is well-defined. Means we have to show that the supremum mod of xn minus yn, where n varies from 1 to infinity, must be non-negative real number. For this mod of xm minus ym, this is less equal mod xm plus mod ym by triangle inequality. This is less equal supremum of mod xn 1 less equal n less than infinity plus supremum of mod yn 1 less equal n less than infinity. And this must be less than infinity since xn and yn are bounded sequences. Yn are bounded sequences. Means supremum of mod xn is equal to some positive number m, supremum of mod yn is equal to m dash exist, and their addition is m plus m dash is greater or equal mod of xm minus ym. Therefore supremum of mod of xm minus ym, where 1 less equal m less than infinity, this must be less than infinity, and therefore L in D infinity of x bar y bar belongs to 0 infinity. Implies D infinity is defined. Now we have to verify that D infinity satisfy all axioms of matrix. So we will verify 4 axioms of matrix one by one. So first axiom, we have to show that D infinity of x bar y bar greater or equal 0. So m1 for x bar y bar belongs to L infinity, mod of xn minus yn greater or equal 0 for every n, implies supremum of mod xn minus yn, where 1 varies from 1 to infinity, this must be greater or equal 0, and therefore D infinity of x bar y bar greater or equal 0. M2 axiom, d infinity of x bar is equal to supremum of mod of xn minus xn 1 less equal n less than infinity, but xn minus xn is 0 for every n, means this set is just singleton set 0, its supremum remains 0. For x bar not equal to y bar sequence, xn is not equal to yn for at least one n. Implies mod of xn minus yn greater than 0 and mod of xm minus ym greater equal 0 for all m. Implies supremum of mod of xn minus yn, where one varies from, or if I take here j 1 less equal j less than infinity, mod xj minus yj, this must be greater than 0 because mod of xn minus yn is one term among these set for which we are taking supremum, and other terms are greater equal 0. Therefore, supremum must be greater equal 0. Therefore, d infinity of x bar y bar greater than 0 for x bar not equal to y bar. From this, d infinity of x bar y bar is equal to 0 if and only if x bar is equal to y bar. Now, we have to verify M3, that is symmetry axiom. M3 symmetry. So for this, d infinity of x bar y bar is nothing but supremum of mod of xn minus yn, 1 varies from 1 to infinity, and this is equal to supremum of mod yn minus xn, because xn yn are real numbers, and this is nothing but d infinity of y bar x bar by definition of d infinity metric or function. M4 triangle inequality. To show d infinity of x bar y bar less equal d infinity of x bar z bar plus d infinity of z bar y bar, or z bar is equal to zn belongs to L infinity. For this, mod of xn minus yn is written as mod of xn minus zn plus zn minus yn. What I am doing, I am subtracting and adding nth component, nth term of sequence zn. Then by triangle inequality, this is less equal mod xn minus zn plus mod of zn minus yn. Then this must be less equal supremum of mod of xj minus zj 1 less equal j less than infinity plus supremum of mod of zj minus yj 1 less equal j less than infinity for every n, as we are not taking any restriction on choice of n here. Therefore, supremum of mod xn minus yn 1 less equal n less than infinity is less equal d infinity of x bar z bar plus d infinity of z bar y bar, and therefore d infinity of x bar y bar is less equal d infinity of x bar z bar plus d infinity of z bar y bar. And as there is no any restriction on choices of x, y, z, means for any three sequences x bar, y bar, z bar belonging to L infinity. So thus we verified d infinity satisfy all axioms of metric. Thus d infinity satisfy all axioms of metric. Therefore L infinity with d infinity is metric space. Now in this example, L infinity is taken to be set of bounded real sequences. If I take L infinity to be set of bounded complex sequences, and if I take d infinity of x bar y bar function which is defined in this way, then it must be metric for L infinity, and it becomes metric space with respect to that defined function. Now we'll take other example. You are familiar with concept of bounded function, bounded real function. What is bounded function? A function f from x to r is bounded if there exists some m greater than 0 such that mod of fx less equal m for every x belonging to x. Whatever choice of x set may be, that f assigns every element of x to real number. And as I am talking about the real number, fx is a real number, so its modulus exists and it is non-negative real number. So if for every x mod fx is less equal m, then we say that that function is bounded function. Now if I take the class of all bounded function defined on non-empty set x, on that can we define some metric? Yes, it is possible. So we'll take that type of example. So let x be non-empty set and b of x is equal to set of function f such that f from x to r is bounded function. So this is nothing but class of bounded function, class of bounded real valued function defined on x. For fg belongs to bx, we define d infinity again, d infinity of fg is equal to supremum of mod fx minus gx. Now as f and g a real valued function means fx and gx are real number, the difference is also real number, modulus is a real number, so I can talk about its supremum. So this is a real number, no doubt. Now we have to check whether it is it exists or not. If it approaches towards infinity, then the d infinity function is not defined for b of x. Okay. So step first, to show d infinity is defined. Now since fg belongs to class of bounded function defined on x, implies fg are bounded functions. implies there exists some m1 m2 greater than 0 such that mod fx is less equal m1 mod gx less equal m2 for every x belongs to x. Now mod fx minus gx, this is less equal mod of fx plus mod gx is less equal m1 plus m2 less than infinity for every x belongs to m x. This implies f minus g is bounded function on x and therefore d infinity is defined. Therefore d infinity of fg is defined. So d infinity of fg is a non-negative real number. Now we have to show that d infinity is metric for bx. Means we have to verify 4 axioms of metric: positivity axiom, then symmetry and triangle inequality. We'll verify one by one. M1 for x belongs to x, mod fx minus gx is greater equal 0. Implies supremum of fx minus gx which exists x belongs to x. This must be greater equal 0. Therefore d infinity of fg greater equal 0. M2 for f equal to g, d infinity of fg is equal to d infinity of ff. This is equal to supremum of mod fx minus fx where x belongs to x. This must be supremum of this set contain only 0 and we are taking its supremum, so it becomes 0. For f not equal g, fx is not equal to or fy not equal to gy for at least one y belongs to x, and therefore mod fy minus g of y must be strictly greater than 0. This implies supremum of mod fx minus gx, x belongs to x, this must be greater than 0 since for x is equal to y, fy minus gy greater than 0 and other terms are greater equal 0. Therefore d infinity of fg greater than 0 for f not equal to g. Thus d infinity of fg is 0 if and only if f equal to g. Now we have to verify symmetry axiom. Symmetry. So for this, d infinity of fg is equal to supremum of mod fx minus gx where x values in x. We know that mod fx minus gx is same as mod gx minus fx. So this is supremum of mod gx minus fx. Then it is nothing but d infinity of gf. The symmetry axiom hold. Now we'll prove triangle inequality parallel to what we have done for L infinity metric space. M4 triangle inequality. to show d infinity of fg is less equal d infinity of fh plus d infinity of hg, h belongs to fx, bx. It is bounded function from x to r. So for this, mod of fx minus gx is equal to mod fx minus hx plus hx minus gx for any x belongs to x. Then by triangle inequality, this is less equal mod fx minus hx plus mod hx minus gx. Mod a plus b less equal mod a plus mod b for any two real numbers a and b, and then this is less equal supremum of mod fy minus hy, where y varies in x, plus supremum of hx minus gx, hy minus g of y, where y varies in x. This implies mod fx minus gx less equal d infinity of fh plus d infinity of hg for every x belongs to x, and therefore supremum of mod fx minus gx, x belongs to x, this must be less equal this, therefore d infinity of fg less equal d infinity of fh plus d infinity of hg. Thus d infinity satisfy all axioms of metric, and therefore bx together with d infinity is metric space. Now we are familiar with continuous function defined on closed interval AB. We are also known that any continuous function defined on closed interval AB, that is, if f from closed interval AB to R is continuous function, then it is bounded and it attains its supremum, and that supremum is nothing but the maximum of range set of that bounded function f. So on set of continuous function defined on closed and bounded interval AB, we will define metric now. Next example, CAB is equal to set of f functions such that f from A to R is continuous function. So it is class of continuous function defined on closed and bounded interval AB. For fg belongs to CAB, means if f and g are continuous function from AB to R, we will define d infinity of fg is equal to maximum of mod fx minus gx. X belongs to AB. Then CAB with this d infinity is metric space. In previous example, I am replacing that supremum by maximum here, and x belongs to AB, x is replaced by close interval AB. Why we are replacing that supremum by maximum? As f and g are continuous function, fg continuous implies fg are bounded functions. And attains supremum infimum. Attains supremum infimum. Means what is that supremum of fx? Mod fx, x varies in AB. It is nothing but the maximum of range set, and that's why again difference of two continuous functions is continuous. Means if f and g are continuous function, then f minus g is continuous, and that f minus g is also bounded function which attains its supremum, and that supremum is nothing but maximum. That's why that supremum is just replaced by maximum here. And what we have done for previous example, that is b of x with respect to d infinity is metric space. We'll do same thing to prove that the CAB with d infinity is metric space. Okay, so solution by previous example. Bx with d infinity. Okay, so using that solution, we'll easily prove that this is metric space. Only you have to replace maximum by supremum by maximum word, and you have to just write reasoning. If f and g are continuous function, their difference is continuous. Continuous function on closed and bounded interval is bounded function as well as it attains its supremum. That supremum is nothing but the maximum of range set. Only you have to use this idea to prove this CAB with d infinity is metric space. Is it clear? Now we'll go to next example. We know that every continuous function on closed and bounded interval is Riemann integrable. So by using integrability, we can define one more metric on this. For fg belongs to CAB, dp of fg is equal to integral of a to b mod of fx minus gx to the power p, and integral raised to 1 by p, where 1 less equal p less than infinity. Then dp is metric for CAB. So we'll explain solution of this in detail. Since fg belongs to class of continuous functions on AB, implies fg are Riemann integrable functions on AB, and therefore f minus g belongs to class of Riemann integrable function on AB. Implies mod of f minus g to the power p also belongs to class of Riemann integrable function on AB, for p belongs to close open interval 1 infinity, whatever choice of p may be, which is fixed. And therefore dp of fg is equal to integral of a to b mod fx minus gx to the power p whole thing raised to dx whole thing raised to 1 by p exist. Therefore dp is defined. dp is defined. Now we have to verify axiom. This is our step 1. What is step 1? dp is defined function from CAB cross CAB to set of real number. Okay. Step 2, dp is metric. For that, m1 so since mod of fx minus gx raised to p is greater or equal to 0 for every x belongs to AB, implies integral of a to b mod fx minus gx to the power p dx greater or equal to 0, and therefore d infinity of fg is equal to integral of a to b mod fx minus gx raised to p dx whole thing raised to 1 by p must be greater than or equal to 0. So thus first axiom is satisfied by d infinity or dp, not d infinity, dp. m2 dp of ff is equal to integral of a to b mod fx minus fx raised to p dx whole thing raised to 1 by p, which is nothing but integral of a to b 0 dx raised to 1 by p, which is 0, because integral of 0 is 0, definite integral. For f not equal g, fc not equal to g of c for at least one c. At least one c belongs to f. Moreover, fg are continuous functions implies f minus g is continuous function on AB, continuous, and mod of fc minus g of c greater than 0, fx minus gx greater than 0 in n delta c is equal to c minus delta to c plus delta for some delta greater than 0. As f minus g is continuous function on AB, so f minus g is continuous at c implies it must be continuous in at least some neighborhood about c, and mod fx minus gx is greater than 0 for every x lying between n delta c. And therefore integral of a to b mod fx minus gx raised to p dx, I can write this as integral of a to b minus c minus delta mod fx minus gx to the power p plus integral of c minus delta to c plus delta mod fx minus gx to the power p plus integral of c plus delta to b mod fx minus gx to the power p. Now, over this a to c minus delta mod fx minus gx is non-negative valued function, so its integral is greater or equal to 0. Again on c plus delta to b, this mod fx minus gx is continuous and it is greater or equal to 0. Therefore, its integral value is also greater or equal to 0. And over c minus delta to c plus delta, mod fx minus gx is strictly greater than 0. F of c is positive there. So, by property of Riemann integrable function, this integral must be positive. Non-negative number plus strictly positive number plus non-negative number, this must be greater than 0 plus positive plus 0. Okay, so this is greater than 0. And therefore, the infinity of fg is strictly greater than 0 for f not equal to 0. Or the infinity of fg is nothing but integral of a to b mod fx minus gx to the power p dx. This is positive, so if I take its pth root, it is also positive for f not equal to g. Thus, the infinity of fg is 0 if and if f equal to g. M3, the infinity of fg is equal to integral of a to b mod fx minus gx to the power p dx whole thing raised to 1 by p, and again this mod fx minus gx is same as mod gx minus fx. So I can write this as integral of a to b mod of gx minus fx to the power p dx whole thing raised to 1 by p, and which is nothing but by definition of dp. I am using d infinity, just take it to be dp now, which is dp of gf by definition of dp. So symmetry axiom. M4 triangle inequality. Triangle inequality. Okay. So to show dp of fg less equal dp of fh plus dp of gh. So for this, dp of fg is equal to integral of a to b mod of fx minus gx to the power p dx whole thing raised to 1 by p. Again I will insert hx, add and subtract here. So we will get this is to be integral of a to b mod fx minus hx plus hx minus gx to the power p whole thing raised to dx whole thing raised to 1 by p. Now by using Minkowski's inequality, this is less equal integral of a to b mod fx minus gx raised to p dx whole thing raised to 1 by p plus integral of a to b mod of, hx mod hx minus gx whole thing raised to p dx whole thing raised to 1 by p by Minkowski's inequality. And then this is nothing but d infinity of h plus d infinity of hg. Thus d infinity, dp, thus dp satisfy all axioms of metric. And therefore CAB If dp is a metric space where p varies from 1 to infinity. So in this way we have taken most of the examples of metric spaces which we require while studying concepts like open set, closed sets, continuous functions, homeomorphism, etc. Cauchy sequences, convergence sequences in metric spaces. We require these examples. So with this example, we'll stop here, and in next lecture, again, we'll take examples of functions which are not metric, which are metric, but we'll construct that metric from old matrix. Means we'll construct new metric from given matrix in next coming lectures. We'll stop here. Thank you.